Gravitational force and the complete lack of emitted light represent boundaries where established principles of physics cease to function. These extreme conditions are most prominently found in black holes, regions of space so dense and powerful that not even light can escape their grasp. First envisioned by the legendary physicist Albert Einstein in 1916 as a byproduct of his groundbreaking general theory of relativity, black holes were, for many decades, regarded as mere theoretical curiosities. For a long time, they existed only in the equations and imagination of physicists. The scientific community largely considered them speculative due to the lack of observational evidence and the extreme nature of their properties. It wasn't until significant strides in observational technology during the 20th century that the possibility of detecting black holes became not only feasible but inevitable. With improvements in radio astronomy, X-ray detection, and telescope resolution, the hunt for these invisible giants began in earnest. A major breakthrough occurred in the 1960s when astronomers, while investigating the Ceres constellation, stumbled upon an unusual celestial phenomenon. They identified an anomalous star, a radiant blue star emitting intense and high-energy X-rays. This peculiar star exhibited an orbital motion around an unseen companion, puzzling researchers who could not account for the invisible gravitational force at play. After extensive analysis, it was determined that the visible star was in a gravitational bond with an immense and unseen object, what would later be identified as a colossal black hole, subsequently named Ceres X1. This landmark discovery offered the first solid confirmation of black holes' existence and launched a new era of astronomical research focused on these enigmatic cosmic features. The discovery of Ceres X1, situated approximately 6,000 light-years from Earth, was not just a validation of Einstein's equations but also a harbinger of how little we truly understood about the universe. Ceres X1 possesses mind-boggling properties. Its mass is concentrated within a volume so small and dense that the gravitational influence it exerts is virtually inescapable. The escape velocity required to break free from its gravitational pull exceeds the speed of light, rendering escape physically impossible according to the laws of relativity. This defining trait encapsulates the essence of what makes a black hole so mysterious and compelling. Since the discovery of Ceres X1, researchers have uncovered countless more black holes scattered across the vast expanse of the universe. Current projections suggest that our very own Milky Way galaxy may harbor over 100 million black holes. These range from relatively modest stellar mass black holes, formed from the remnants of collapsed massive stars, to incomprehensibly massive variants, supermassive black holes, residing at the centers of galaxies and shaping galactic evolution. Despite their elusive nature, which complicates any form of direct observation, astronomers have developed clever indirect methods to detect and study black holes. These methods include tracking the motion of nearby stars, detecting X-rays emitted by matter as it is consumed by the black hole, and, more recently, observing gravitational waves caused by collisions between black holes. Black holes' impact extends well beyond their immediate surroundings. Their gravitational pull can dictate the orbits of stars, influence the flow of interstellar gas, and even determine the formation of new stellar systems. When an object ventures too close to a black hole, it crosses a perilous threshold known as the event horizon. This is the point of no return. Once crossed, not even light can escape the gravitational grip of the black hole. Beyond this threshold, gravitational forces dominate completely, subjecting objects to extreme tidal stresses. This violent process, referred to as spaghettification, stretches matter into elongated filaments, somewhat reminiscent of strands of pasta. The gravitational gradient is so intense that it rips apart the internal structure of any object that crosses into the event horizon, tearing it molecule by molecule until it is finally absorbed into the singularity at the black hole's core. This singularity is a point of infinite density where the known laws of physics break down entirely. The dramatic interaction between black holes and the matter they consume starkly illustrates the formidable power these cosmic phenomena wield. While black holes offer unparalleled opportunities to test the boundaries of theoretical physics, they remain cloaked in mystery. Scientists across the globe continue their tireless efforts to unlock the secrets of black holes, driven by a relentless ambition to better comprehend the very fabric of space-time and the fundamental nature of gravity. These celestial entities, though located light-years away, the nearest known black hole being roughly 2,500 light-years distant, continue to provoke awe, questions, and concern due to their immense gravitational influence. In 2021, researchers achieved a historic milestone when they captured the first direct image of a black hole, specifically the one at the heart of the M87 galaxy. This unprecedented achievement, made possible through the Event Horizon Telescope, offered valuable insight into the internal structure and physical properties of black holes. The image of the black hole in the M87 galaxy revealed that these mysterious entities are far from being featureless voids. Instead, they possess intricate layers and structures that reflect complex physical phenomena at play. Careful analysis of the image revealed three key regions within a typical black hole. The outermost region is the event horizon, the definitive boundary beyond which escape becomes impossible. Inside the event horizon lies the photon sphere, where light itself is trapped in perpetual orbit due to the intense gravitational field. At the core of the black hole is the singularity, the mysterious point where space-time curvature becomes infinite and all known laws of physics collapse. This central singularity remains one of the greatest mysteries in modern science, ushering researchers into realms governed not by observable phenomena but by speculation and theoretical constructs. Black holes, though sharing this foundational three-layer model, exhibit a wide range of characteristics and behaviors, defying any simplistic classification. Some rotate at nearly the speed of light, while others may exist in binary systems or serve as the engines of quasars and active galactic nuclei. Consequently, traditional scientific methods often prove inadequate for their study, prompting the development of novel approaches, including computer simulations, advanced gravitational wave detectors, and space-based observatories. Since the immense gravitational fields of black holes make direct exploration physically impossible, indirect methods remain the primary mode of investigation. Any spacecraft attempting to enter a black hole would be instantaneously crushed by the forces within, disappearing without a trace, an outcome that highlights the inaccessibility of these cosmic giants. Nevertheless, scientists persist. Fueled by insatiable curiosity and a determination to uncover the truth behind these celestial leviathans, researchers continue to refine their models and gather data. Various hypotheses attempt to explain the genesis and behavior of black holes, many of which are linked to stellar evolution and broader cosmological processes. Notably, NASA's prolonged observation of M87's core has delivered compelling support for the presence of a supermassive black hole influencing vast regions of space. Despite the considerable difficulties posed by black hole research, the scientific community remains undeterred. They pursue deeper knowledge with vigor and hope, viewing the study of black holes as far more than a mere academic challenge. It is, in truth, a profound journey to understand the very essence of existence itself. Roy Kerr's revolutionary work in 1963 introduced a groundbreaking concept to black hole theory by proposing a model for rotating black holes. This model contradicted many earlier assumptions, which often imagined black holes as static, non-rotating singularities. Central to Kerr's model was the concept of the ergosphere, a peculiar zone around a spinning black hole where space itself is dragged along by the black hole's rotation. This dragging of space-time not only complicates the structure of black holes but also offers insight into how rotation can influence the dynamics of gravitational collapse. The ergosphere balances out gravitational collapse and prevents additional inward fall in certain areas, creating a region of unusual behavior that suggests deeper mysteries may be at play. Perhaps the most fascinating idea to emerge from Kerr's theory was the possibility of an Einstein-Rosen bridge, more commonly known as a wormhole. A wormhole, according to general relativity, might serve as a bridge through space-time, potentially linking distant regions of the universe, or even alternate universes. This concept arises from the modern understanding of the universe as a four-dimensional space-time fabric, which bends and curves in response to massive objects. Wormholes are envisioned as tunnels through this curved fabric, offering hypothetical shortcuts across great cosmic distances. Yet, despite their theoretical allure, the practicality of wormholes remains highly uncertain. Numerous theoretical barriers, such as instability, quantum interference, and intense radiation, render their existence and utility speculative at best. Though tantalizing, the notion of faster-than-light travel via wormholes runs into significant problems. Einstein's own theories imply speed limits that even wormholes may not bypass. Nevertheless, the allure of such cosmic gateways continues to inspire researchers, inviting dreams of traversing galaxies and discovering parallel worlds. Wormholes, in their theoretical elegance, symbolize the unexplored potentials of the universe and the unending human quest to reach beyond the known frontiers. They represent both the promises and the paradoxes that lie at the intersection of science fiction and cutting-edge theoretical physics. The pursuit of a unified theory that marries gravity with quantum mechanics, a so-called theory of everything, has become one of modern science's greatest ambitions. At the forefront of this movement stands the celebrated physicist Myoku, whose pioneering efforts have helped shape the development of superstring theory. This advanced theory departs from the idea of point-like particles and instead proposes that everything in the universe is composed of one-dimensional vibrating strings. Each elementary particle corresponds to a unique mode of vibration, much like the notes produced on a violin string. According to superstring theory, the cosmos can be likened to a grand symphony of resonating energy patterns, where all matter and forces arise from the harmonics of tiny strings. Importantly, superstring theory offers potential explanations for some of the most bizarre and puzzling features of black holes, wormholes, and other anomalies predicted by Einstein's equations. However, the framework introduces new challenges by requiring the existence of additional dimensions, far beyond the familiar 3 spatial and 1 temporal dimension. These extra dimensions, the eyes to be folded tightly in upon themselves, elude direct observation. Nonetheless, they are believed to shape the very structure of our universe. Analogies such as fish navigating a 2-dimensional lake help illustrate how higher dimensions might exist unnoticed, influencing our world without ever being directly perceived. The mathematics behind superstring theory has also reignited interest in the deep relationship between physics and geometry. It reveals intricate links between numerical patterns and physical phenomena, suggesting that the universe itself may be governed by mathematical beauty. While still theoretical, the implications of superstring theory are profound. Despite its intellectual sophistication, the theory remains experimentally unverified, primarily due to the hidden nature of extra dimensions. As a result, it currently resides within the domain of abstract mathematics and theoretical speculation. Yet its conceptual richness continues to attract thinkers from multiple disciplines, challenging them to rethink the architecture of the universe and opening entirely new realms of inquiry. In confronting the enigma of quantum black holes, physicists have faced a challenge that strikes at the very core of modern science. For years, attempts to reconcile quantum mechanics with gravity have fallen short. Edward Witten, a prominent voice in the field, once referred to superstring theory as a 21st century idea that landed in the 20th century. Recently, however, some progress has emerged. Independent research groups have demonstrated that string theory might solve certain black hole puzzles, at least in simplified 2-dimensional models, as opposed to the full 10-dimensional versions. While this marks a meaningful step forward, the ultimate answer remains elusive. The journey toward a fully unified theory continues, drawing scientists deeper into the mysterious interplay between reality and abstraction. Black holes, with their immense power, unfathomable complexity, and capacity to bend the very laws of physics, offer vital clues to the nature of the cosmos. But they also underscore the limits of human understanding. As our technology and theories evolve, so too does our capacity to peer further into these cosmic abysses, to unravel the deepest truths of our existence, and to glimpse the hidden structure of the universe itself. In confronting the enigma of quantum black holes, physicists have faced a challenge that strikes at the very core of modern science. For years, attempts to reconcile quantum mechanics with gravity have fallen short. Edward Witten, a prominent voice in the field, once referred to superstring theory as a 21st century idea that arrived early, capturing both its promise and its current inaccessibility. The marriage of quantum theory and general relativity remains elusive because these two great frameworks of physics, each incredibly successful in its domain, appear fundamentally incompatible in the presence of extreme gravitational fields, such as those found in and around black holes. At the quantum level, particles behave probabilistically and seem to exist in a state of constant fluctuation. But general relativity demands smooth, predictable spacetime curvature. When black holes are introduced into the quantum framework, paradoxes erupt, none more famous than the black hole information paradox. Stephen Hawking's revolutionary work in the 1970s led to the discovery of what is now called Hawking radiation, a theoretical prediction that black holes are not entirely black. Instead, they emit a faint glow due to quantum effects near the event horizon. This radiation implies that black holes could eventually evaporate and disappear. However, if black holes vanish, what happens to the information they consumed? According to quantum mechanics, information cannot be destroyed, it must be preserved in some form. But general relativity says otherwise when dealing with black holes. Thus emerged one of the most pressing quandaries in theoretical physics. If information falls into a black hole and the black hole eventually evaporates, does the information vanish forever? This paradox challenges the very foundation of both quantum theory and cosmology, prompting decades of debate and countless attempts at resolution. Several competing hypotheses have been proposed. Some suggest that information may be encoded on the event horizon itself, a theory called the holographic principle. This idea, most notably advanced by physicist Juan Maldacena, posits that everything within a volume of space can be described by information encoded on the boundary of that space. In black holes, This principle suggests that the information consumed by the black hole is somehow imprinted onto its surface area, not lost inside its core. Others propose that information might be released slowly in the form of subtle quantum correlations during the emission of Hawking radiation. Then there are more radical ideas, that black holes might serve as gateways to other universes, or that information is preserved in alternate realities or dimensions, consistent with some interpretations of string theory and the multiverse hypothesis. These theoretical insights have forced physicists to reconsider the nature of reality itself. The concept of space and time as continuous and absolute may no longer hold in the extreme conditions found within black holes. At the Planck scale, the smallest measurable unit in the universe, quantum fluctuations dominate, and space-time becomes a frothing sea of probabilistic states. Black holes may serve as cosmic laboratories, offering unique windows into this turbulent, high-energy regime where our current understanding breaks down. As scientists continue to refine their models, hopes remain that future advances in quantum gravity, possibly through the still-maturing framework of M-theory, will finally deliver a coherent understanding of these mysterious objects. Observational breakthroughs continue to guide theoretical advances. In recent years, instruments such as the Laser Interferometer Gravitational Wave Observatory, LIGO, and its European counterpart, Virgo, have detected ripples in the fabric of spacetime produced by merging black holes. These gravitational waves, first observed in 2015, confirmed another key prediction of Einstein's general relativity and opened an entirely